nanohub.org.
Online simulation and more for nanotechnology.
I'm going to speak a little louder today than usual, and it's because partially to improve the audio quality, but also because it's a very exciting topic, which is basically the growth of optical communication networking going forward. And so the reason why this is an important topic, as you can imagine, is we have more and more demands for communications. And just to kind of put this in a very long-term historical perspective, in fact, there is a recent paper that looked all the way back to like the early 1800s at basically how quickly could we communicate information per, like in bits per second, essentially, like across the whole world, more or less. And so basically what this is showing is that the best results, in the 1800s, like were with telegraphs, and obviously it's not very high bandwidth, but they were able to get maybe like 10 megabits per second. Okay, not a huge amount. Okay, so this is megabits, not bytes. Okay, so it's probably like 1 megabyte per second, roughly. So not a lot, but as you can see, of course, the technology improved like just for cable lines. And so this is a topic that's covered sometimes in undergraduate ECE curriculum. But then there was, of course, a big switch, maybe like in the late 60s, early 70s, to optical telecommunications. And then, while obviously it had already been increasing at a fast rate, it maybe even arguably went faster once you got to that point. And more recently, it's still been increasing. Okay, so don't be fooled by the scales. I mean, this is like a log-log scale, so it looks actually a little bit like things have rolled over to some extent. It was not necessarily quite as rolled over as it looks, because this is just going over like a span of about 10 years. So of course, you're not going to have like, many orders of magnitude improvement over 10 years. But you can see that like the capacity has increased to the point that now the best reported results are in the order of like tens of terabits per second, right? So on the order of like maybe over 1 to 10, maybe terabytes per second, which is a tremendous amount of capacity. But we still are confronted with the problem today that, videos can buffer slowly. We may have delays in basically email communication that in tight time situations can prevent us from doing what we want to do. And then, of course, there's a lot of discussion about implementing new types of technologies that would probably even use more bandwidth, such as virtual reality, right? So if you think videos consume a lot of bandwidth, imagine virtual reality bandwidth, right? That's going to be tremendous. So for all those reasons, it's really important to think about what the future of telecom looks like, rather than just kind of taking everything we've done in this class so far as basically like a static entity and just like maintain it forever in its current state, right? There's a lot of things that can be done. And so roughly speaking, there are 3 categories of things that we can really do. And the first category is actually upgrading existing hardware. But I just want to give you this broad overview. So the first topic, upgrading existing network hardware. So that's all about kind of taking the infrastructure we have to a large extent, but then making it work better. So basically enabling us to upgrade like individual components in the systems without necessarily ripping everything out and starting over again, okay? And then something that's kind of a little bit different, but analogous in terms of the concept, is essentially improving the communication protocol. And to some extent, there's interaction with the hardware, but fundamentally, like this is more kind of a software type thing, where basically you're using like better algorithms and better software programming to basically make the existing hardware work better, or potentially to upgrade both the hardware and software in tandem to get the bandwidth to increase significantly. But then this final concept that I'll basically just talk about briefly today, and then we'll follow up more on like later in this week, will be essentially like what are some novel network concepts that would be going beyond kind of like more incremental changes in the first 2 categories. And so it's like really disruptive concepts. With that said, of course, it's not clear if any of these will be successful, like on a broad scale, but certainly interesting to think about. Okay, so I already explained that. So on the hardware side, okay, so like obviously in principle you can upgrade everything, so I don't want to exclude anything, but I wanted to focus on things that I think a lot of people are talking about trying to upgrade. Okay, so just to keep in mind, this is not an all-inclusive list of every possible hardware upgrade, but these are like the things that could really move the needle in terms of capacity and reliability of the network. Okay, so I'll kind of like try to go through each one of these, but let me just briefly summarize what each is before I go into depth. So basically the polarization multiplexing, so that's basically using different polarizations on the same wavelength on the same physical line. Coherent detection, also known as heterodyne detection, that's all about basically having your data stream basically interfere with some sort of carrier frequency, so then you can translate into the radio frequency domain. And then that gives you like extra information about the phase of the system. So that's like obviously more information than you would have otherwise. And of course, some of the industry has moved in that direction, but there's more that can be done on that. Another thing that's also starting to become more common is this dispersion-compensated fiber. So they are basically, as you recall, like the time delay between different parts of the signal limits your bandwidth. And so this is all about basically removing that extra time delay associated with dispersion as much as possible. Multimode fibers, basically a concept there is just to, rather than use single mode fibers like we had talked about earlier, actually move like into the multi-mode domain. And of course, there are some challenges there, so I'll try to explain those. And then digital signal processing, this is really about moving from like analog information to something that's digitized to immunize yourself against noise. And of course, this also is something that's starting to be more widely adopted. Okay, so going through each of these things. So dispersion-compensated fibers. Okay, so basically this is like kind of conceptually one of the simplest ideas. So it's essentially like if you have dispersion, like let's say dispersion is minus 100, okay? And then you go through 10 kilometers of this. Then if you had a dispersion of plus 1,000, then 1 kilometer would basically cancel out the dispersion to the lowest order, okay? So it's not exact cancellation because there are also nonlinear effects, but in principle, like just adding this extra length of fiber can get rid of a lot of the dispersion you'd have otherwise, right? And so this means you can still keep your existing infrastructure, but now you have this extra fiber, and maybe it adds a little loss, but it also increases your bandwidth at the same time. So this is like something that I alluded to earlier, but just to say that this is like going to be definitely a big move to using both essentially like extra fibers to compensate for the existing dispersion. But then there's also basically like dispersion-free fiber concepts where like within the wavelength range you care about, like you just keep dispersion as low as possible, so you don't even have to compensate for it. So then that's even like the next step beyond that. Now, unfortunately, those kind of like ultra low dispersion fibers are not as easy to find at low cost. So I think dispersion compensated fibers are like the next thing. And then the next thing would be basically dispersion-free fibers, or ultra low dispersion fibers, maybe you can call them. On coherent detection, so I had mentioned that like this heterodyne detection, basically the concept is very simple, which is just that you have like some input frequency F1, okay, so this is your input, and then you have basically some optical source at a frequency F2. So then the idea is basically it's going to have two outputs through four-wave type mixing. There's going to be basically like F2 minus F1 frequency output, and then there'll be a F1 plus F2. Okay, so if F1 and F2 are pretty close to each other, but this is like a well-calibrated reference, now what you've done is actually, with this F2 minus F1 channel, you've taken something that was like at ultra high frequency, like let's say this is 200 terahertz, and this is like 201 terahertz, just to keep the math easy, right? Then this basically becomes 1 terahertz, and then this becomes like 401. But you can even go further and say, instead of 201, maybe 200.1, so now this becomes 0.1. So you can just lower it as much as you want, basically, by doing at least roughly what this frequency is, and having well-calibrated reference. Now you can actually start outputting stuff that's more like in the radio frequency domain. And so being able to do that is very critical to being able to coherently analyze all your output. Okay, so now you actually can use multiple phases in the same information. Because remember, before we talked about phase shift keying, and before the idea was basically you have 0 or pi phase shift. And now in principle, you can have a number of different phase shifts, basically arbitrary choice of phase shift. So that's actually very exciting because now you can squeeze a lot more information into each specific wavelength, each channel that we talked about in WDM, right? So this is definitely going to be important. And so there are so many advantages that I was basically running out of room to list all of them. But I think the most key ones are that there's going to be increased sensitivity in the system because now you can use much slower detectors to detect your signal, right? So that alone is a huge plus because like you may or may not know, like a lot of these detectors, once you go up to ultra high frequencies, are going to have trouble basically detecting your input signals unless they're very strong. But once you drop down to lower frequencies, much easier. So sensitivity alone is a big advantage. But then second is now your capacity is higher because you squeeze more information in, as I said. Third, actually, is you can potentially do dispersion compensation, which is potentially complementary to the other dispersion compensation I mentioned previously with the dispersion compensating fiber. So then doing both dispersion compensation fiber plus the coherent detection is really a big win. And then that, of course, in turn increases your signal to noise ratio by a huge amount because now you have a much stronger signal and you have less noise because you've subtracted some of the noise from the system from dispersion. And also, the overall ratio just becomes much more favorable, right? On both sides, numerator and denominator. And of course, another thing that's very important is that this actually enables you to do other stuff that's like very consequential as well. And of course, I think the most important thing you can do is basically this digital signal processing, which I'm going to explain shortly in detail. But let me talk about polarization multiplexing because that'll help you understand the DSP part first. Okay, so basically, polarization multiplexing is important because here, basically, we're just saying, just in the simplest case, maybe we have a fiber, okay, and it has like this, let's say mode like this, okay? So this is plus or minus, but we also have a mode that looks like this, right? And I think that was something I talked about on the first day of class, basically, like why do we have two modes, like if it's a quote-unquote single mode fiber, right? so that doesn't sound very consistent. But the point was that basically, if this is perfectly circular, then these two modes are degenerate. And we said that if you basically make it slightly elliptical, you can break the symmetry, so then there are different frequencies. But another way to actually address this is to try to put different information onto each of these polarization channels, okay? Which sounds great, like in principle, because now it's like, okay, we have double the information and there's no real penalty. But the challenge is basically there's polarization drift. And so what does that mean? I mean, in practice, like when you send light through these fiber optic cables, then there are a lot of things that can basically cause polarization mixing. So for example, any asymmetry in the fiber or any bending, any stress that's applied to the fiber. So like basically experimentally, a lot of things can go wrong. So if you're sending it over like hundreds of kilometers, then you may have a complete mix of polarizations. In particularly, you can get drift in both polarizations. So Fortunately, though, there are ways to basically address the polarization states. And so digital signal processing is really the key advance that allows you to use polarization states in a meaningful way. Let me explain that first, maybe, and then I'll talk about the other stuff. Okay, so basically, how does this digital signal processing concept work? And so this paper from a few years ago kind of shows the idea. So before we had talked about on-off keying, more or less. So that was kind of down here. And basically, there are two issues with on-off keying, right? So one is, of course, it's either on or off, so you just get one bit. Okay, so that by itself is a big problem because we're neglecting polarization states and we're neglecting like phase states. Okay, so we're losing both things. And then the second is that we're not necessarily very tolerant to noise because it's kind of like a semi-analog approach. Now, if we go to some of these other strategies, though, okay, so what am I showing here? What are all these little dots? So basically, the idea is that you can use both the polarization and the phase to create like some virtual space of the system. And then you can actually define coding dots, or basically clusters where you want your polarization and your basically your polarization and phase to be. And so the idea is actually you can now split up polarization and phase into multiple bins. And then they have to be separated enough so that there's not much crosstalk, obviously. But this is just showing examples of the ways you can do it. You can basically say there are four ranges, or four like clusters, basically. So it's like 2 in the X polarization, 2 in the Y polarization, for example. Or it could be 2 in X polarization, and then 2 in phase. And so this is actually a very generic concept because it spans both polarization and phase, like mathematically almost the same way. Because you can think of both polarization and phase kind of have like a limited range of values. And so there's always like going to be this finite space in both cases. It's bounded. But now, if you look at what happens is you can just basically start adding more and more of these dots into a given phase and polarization space. Now, what's the limit on this? So obviously there is a limit, which is basically the polarization drift and other noise factors I was talking about earlier. But in this experimental example, the authors showed that even if you do like this 16-bit encoding, right, which obviously is 16 times better than on-off coding, and you look at what's happening at the receiver for a well-designed system, you can still have almost all the dots clustered within kind of their own boxes, right? So there's not really much crosstalk between the adjacent bins, both in the X and Y polarizations that are depicted here. I think this example is showing basically the phase space, and this was like in units of radians. So that's why it has this weird axis from -4 to 4. It's really going like from -pi to pi, I think, in both X and Y. So now you have like essentially like 3 degrees of freedom. So there's the phase in the real part, phase in the imaginary part, and then there's the X or Y polarization. So they use 3 degrees of freedom. So in practice, they actually encode a total of 32 bits across all 3 degrees of freedom, which is way, way higher than the on-off keying, right? So this is basically something that was more experimental concept that had been tested on small scale, but now it's being widely adopted. This whole concept of squeezing as many different bins into this like phase and polarization space as possible. Now, like obviously you're always going to be limited by noise, so you can't like fit infinite number of symbols into each each bin, but at least you can push it pretty hard, especially for shorter distance communications. For longer distance communications, it's obviously going to be more difficult. So there are going to be some trade-offs there for sure. But the point is that now you can actually use this as a powerful tool to optimize the conditions for each given link, right? So that's really the key point. And there's one other thing that we can do besides that on the hardware side that's really interesting, which is go to multimode fibers. And so if you think about like basically squeezing more bits in, then this is like another way to do that, where basically you work above the single mode V number, right? And so now you actually have maybe 2 or more different modes. But remember, we said we go from basically 2 up to 6, like as we cross a V number threshold around 2.45. And so now we can actually have many additional modes that are carrying information. Now, with that said, I mean, there's obviously a big challenge, which is how do you know which modes you're looking at and distinguish those modes, right? So there are actually a couple of things you have to do. You have to either, do very careful design in terms of the connections. So you have to really limit bends and twists to prevent mode mixing between these multiple modes. Of course, the advantage originally of single mode fibers is they're immune to a lot of that. So now you're basically reintroducing that challenge. But the other thing you can do is actually apply MIMO, which I'll explain later in more detail, and or digital signal processing to basically be able to have a little bit of a higher noise tolerance and still have good acceptable bandwidth. Okay, so but I think the really key thing is just to operate just above the single mode V number for now, at least. Like you don't want to go from single mode fiber to like 1,000 modes. Like that's too much. So you have to do it very gradually, like to go up in number of modes so that the technology can keep up. So that was kind of the existing network hardware that I wanted to talk about. Now I want to explain a little more about the communication protocols, because that's kind of related to what I was just talking about, but it's complementary, of course. So particularly the MIMO, which I just mentioned, so which is short for multiple input, multiple output. Try to explain a little bit about that. But I should admit that I'm not a specialist in this area, which in our department is called CNSIP. But at least I can give you a broad overview. And then another thing that's actually very interesting, which is like this kind of, it's actually arguably a hybrid between the hardware and software, which is this space division multiplexing. And this is like space in the fiber, just to be clear, not outer space. So what is MIMO? Okay, so basically the concept in principle is very simple. It's just that you have many sources, many receivers, and then you try to multiplex between all those sources and receivers. So you could say like, oh, okay, didn't we do that already with wavelength division multiplexing? But the answer is this is a little different because now the idea is you use a multipath aspect to basically do the multiplexing. So rather than, in other words, using different wavelengths, it's the same wavelength, but they're taking different spatial paths through the same fiber. Okay, so in principle, this sounds kind of similar to the multimode or few mode fibers, right? But in principle, like this has been demonstrated at least at radio frequencies to work very well. So since all of you probably use Wi-Fi, 802.11n is based on MIMO. And so that was a big advance in terms of the bandwidth in these Wi-Fi configurations. But the concept of MIMO is actually generic enough so that it can also apply to fiber optics in principle. Okay. Now, with that said, I think that the gain is very substantial if it works well. But there is a lot of like software overhead and design needed. And also there's a lot of vulnerability to noise once you start using multipath approaches, because like some of these multipaths may have much lower transmission basically than others, right? So your signal can be highly degraded. If you take a path that's maybe like, not well confined in kind of the core of the cavity, or basically you're exploiting a bend in the cavity or the waveguide to basically, have some path delay, basically can increase the path diversity and therefore the amount of multiplexing gain theoretically possible, but it could also decrease the bandwidth if the delay is too large between different paths. So this is really like a important decision to make in some sense. In the Wi-Fi case, to a large extent, you're really strongly limited by multipath anyway, because as you know, like Wi-Fi doesn't always go in a straight line. There can be all kinds of obstacles that are bouncing your signals around. And that's mostly happening in free space, so it actually makes a lot of sense in that context. In the fiber optic case, usually it's much more tightly confined, so the multipathing is not as great. But of course, if you do digital signal processing, that would give you the best chance to kind of exploit this strategy. And so certainly some people are interested in doing MIMO type approaches for existing fiber optic communications. But I guess we'll see how impactful it is in the long run. And then the other thing that's interesting is the so-called space division multiplexing, which, as I mentioned, is not outer space. But basically, this paper kind of shows you the concept. It came out like just a couple years ago. So you can kind of see, maybe it's easier to look at this index thing. You can see there are basically like two index trenches as you cut a cross section across this thing, like across this way. And so these two index trenches are kind of like their own single mode fibers. Okay, so the idea here is that now you just have a single fiber, but it's effectively like many multi-core fibers at the same time, or single core fibers. Sorry, I should say that again. So it has a bunch of single mode cores, but it has the bandwidth that's more comparable to a multi-core fiber, right? So that's why this has been of great interest to a lot of people, because it kind of extends the existing technology, but it gives you like a big boost in the bandwidth, because now you're taking something that previously just had a single mode, and now you have like maybe 7 times more in this case, or you could have many, many more layers of these fibers, and the physical size of the fiber is not necessarily that much larger. So in principle, this is a huge win. Like, it gives you orders of magnitude improvement. Now, obviously, there are a couple of catches, like A being you need new fibers for everything now. But then B is that you can have crosstalk between these cores, especially if you start packing them in really tight. Then it's more likely to have crosstalk. So it's definitely preferred to have enough spacing to minimize crosstalk as much as possible. And then the other challenge is you can potentially have greater losses in these systems, which is partly driven by crosstalk, but also just driven by the fact that you're much closer to the outer cladding regions, right? And so particularly for those cores on the exterior part, then they might be more susceptible to losses, especially if the mode is not well confined to the core, right? So there are a lot of things that can basically go wrong. So I would say basically this really cool concept, but certainly there's need for more research so that it can be like a commercial product. So I don't think you can buy this today or anything, but there's a lot of people working on this in academia and so on. Okay, so now for the really new and novel network concepts, I want to explain briefly. But first, any questions before I move on? Okay. So these are kind of like the most ideas that are most out there, I would say. Okay. All right, so there's three that I'll try to talk about. The first is solitons. I'll try to explain what a soliton is, but you may have even seen one before. And then air and space-based telecommunications, and then quantum networks. Okay. So these are definitely a bunch of diverse topics. Like, what really unifies them is like nobody's really doing them on a large scale right now. But maybe they can be done in the future. Okay, so solitons, I mean, to be honest, by itself, there's a whole chapter in the textbook. And so I'm probably not going to spend like a whole lecture just on this. But I do want to at least briefly explain like what a soliton is, right? So the way you can think about a soliton, roughly speaking, is that instead of solving like kind of a linear differential equation, which would be essentially like this without this term, okay, you're solving a nonlinear differential equation. And so the key thing is that these nonlinear differential equations, I mean, they can be introduced by many different phenomena, but in the context of optics and optical communications, usually this is like a self or cross-phase modulation term. Okay, so that's really the core of this thing. So if you have a fiber which has nonlinearity, which is basically every fiber, then in principle you can create a soliton. Okay, so this is something that's been of interest for decades, actually. And the reason is very simple, which is that if you look at the broadening of a soliton as it propagates through some medium, okay, this is just from the textbook. It shows that basically the linear case without this term, you'd have this much spreading, more or less, as you propagate over distance, right? So this is like essentially the dispersion we talked about early in the class. But then if you do numerical calculation of the soliton spreading, you can see that it kind of looks like this. And so now you actually have about 3 times less spreading than you would otherwise. And it's more or less the same structure, except you added the nonlinearity, right? So you're not really changing the frequency or the shape of the fiber or anything else. You're just adding this nonlinearity, and then you're creating the soliton mode. And then in principle, the soliton mode cuts down spreading like factor 3 or maybe even more in some more optimistic scenarios. So that's potentially a big deal because now you can fit like 3 times as much bandwidth into the same channel as before, in principle. Okay, so why isn't everybody using solitons today? So there are a few reasons. One is basically that it doesn't always turn out to be as easy to prepare and then to propagate solitons as you might think. There are definitely a lot of details that are needed because it's a nonlinear medium. So that means that if you have any like even subtle change in the nonlinear properties in material or even like loss over spatial propagation, then the soliton may start to break down. And then you can see here in this perturbation chart, if it gets perturbed too much, now it's actually worse. So that shows you that if you're not careful in handling your soliton, now you're just making your bandwidth spreading worse than it was before, which is very unfortunate. So it's not, well, it's robust in some sense. It's also like fragile in another sense, right? Because it's robust in the sense that if you have like the perfect medium and it's completely uniform and everything is designed the way it's supposed to be designed, it works really well. But then, basically any deviation from that is likely to cause a big degradation in the advantage of doing that. And also, you can see just from an experimental perspective, sometimes it might be hard to diagnose because at first it actually looks almost the same, but then it like kind of goes off the rails at the end. So that's another issue, just that it's very nonlinear in terms of its divergence, which is kind of not surprising since it's associated with nonlinearity, that it would have nonlinear divergence as well. But still, it can be frustrating if you're, say, like a telecom engineer in the field trying to get this system to work. But then a third issue is actually power consumption. And so if you look at this equation, like what does the solution look like? So it's basically a hyperbolic secant type function, which more or less looks like a Gaussian to the naked eye, okay? So just think of a Gaussian more or less. That's your solution to this equation, but it also has a characteristic amplitude because there's this u squared term in the equation. So that means that that characteristic amplitude is going to constrain the amount of power you have to use. And so unless you have a highly nonlinear medium, that means you need more power, usually, than the linear communication. Which is not ideal, of course. Like you don't want to use more power if you don't have to, but in this case, you do have to. So unless you make special fibers that have extra nonlinearity, which I don't think most people are doing, then you generally have to use just a significantly greater amount of power. So with that said, I mean, solitons definitely work. Like they've been demonstrated. You can do 100 gigabyte per second communication networks that have been shown in various papers. So I want to say basically solitons are an idea that are always like kind of like getting people's attention in some sense. Like it's not ever going away. But it's also not clear like will there be a space for this technology to play a big role experimentally? Now, I think if it is going to be successful, it would have to be probably for ultra long haul where you don't have access to amplifiers or something like that, right? Because then that's where you, like ultra long haul, and it's a very simple environment, like point to point across like an ocean or something, and you, excuse me, may have trouble installing like amplifiers like in the Mariana Trench or whatever, right? So somewhere that's really bad, like in terms of installation. Like you just need the minimal footprint possible for your fiber. So I think if it's ever going to be successful, it'd be in that context probably. So any questions about the Solitons? Okay. So next topic is air and space-based telecom. So now this is like talking about outer space. So I realize this is confusing because I'm talking about two different types of space. Sorry. But we're trying to cast the net very broadly today. So basically, what is this concept? So it's very interesting in some sense. It was something that Facebook was talking about quite a bit. And so here are the ideas that you have like these unmanned aerial vehicles, okay? And what's happening with these unmanned aerial vehicles, this is not really predominantly an ECE type thing, but what's happened is that because like you have better photovoltaic cells that are much lighter, as well as like advances in materials for composites and in aerospace engineering, plus like obviously some ability to do autonomous piloting. And that's been demonstrated now for both cars and for boats. And so of course, aerial vehicles as well have some degree of autonomy. So now you can actually theoretically fly aerial vehicles like overhead in certain communities and then basically use those to create telecom links. Presumably those also connect to satellites and so on so that you can have a global network. You don't necessarily want to have everybody directly communicate with satellite, of course, because usually you need highly directional communication and high power. Whereas like with these aerial vehicles, they're much, much closer and you don't necessarily need like highly directional communication. So it's kind of like somewhat intermediate between like kind of a standard cell phone tower and something like satellite comms, right? So it's kind of like intermediate link in that communication network, right? So in principle, this is a very cool idea. Now, and these missions can go on for months, and so you can maintain continuous communication for months. And particularly for communities that don't really have any sort of telecoms right now, I mean, this could be breakthrough technology for them. So all this is to say, though, that it's not clear like what the future looks like. This project, Aquila, that was started by Facebook, was kind of downscaled quite a bit, like in the last few months, I believe, like at the end of 2018. And so they've decided that they're not going to create their own aerial vehicles, but they're going to try to partner with other groups that are making theirs. And of course, like as you know, Facebook is predominantly a software company. So going into like kind of this advanced aerospace sector is a challenge, right? Just as it would be for anybody who's coming from outside that area. But nonetheless, I think that while it's a really cool concept and Facebook is downgrading its efforts, they also recognize there is a lot of expertise out there of other groups that are focused on kind of these autonomous aerial vehicles. And so that as this technology progresses, this could actually be a big part of telecoms. And I should add that also, like there are actually two ways to communicate with these aerial vehicles, one of which would be essentially like a free space optical communication approach. And so this could be actually very analogous to the fiber optic networks, but through free space. Obviously, there are some alignment challenges and so on, but the idea is you use laser and then you point it at the vehicle if the vehicle can remain stable or have a well-defined path of flight, right? So that's one strategy. Or the other strategy is obviously to use something more like a cell phone, like a Wi-Fi. And I think short term, that's probably the most feasible but there have been significant advances in terms of tracking and alignment for optical telecoms, so it might be possible long term. But all that is to say that there are going to be like very orthogonal directions that people are coming from to basically expand telecommunication networks. And ultimately, this will impact optical telecommunication, because whether or not they use optics for this part is going to drive like more bandwidth overall. So now, in the last couple minutes, let me just explain briefly about quantum networks. And I think that I'm going to try to have a whole lecture on this, because this is a very rich topic, and certainly it can be very impactful long term. Okay, so in general, what is a quantum network? So quantum network is basically something that allows different actors to communicate in a quantum fashion. And there are actually several variations of this. The easiest one to understand is quantum key distribution. And so here with quantum key distribution, the idea is you have like two people that are communicating A and B, and then they exchange correlated photons with one another. And then if they successfully exchange correlated photons, then they'll satisfy what's called Bell's inequality. And so you know that this is a secure communication and nobody else has been eavesdropping. However, if they look at their data and it doesn't satisfy Bell's inequality, then that means that there was eavesdropping. So that means that if you know whether or not eavesdropping happens, then assuming it's not, then you know that you can create a securely exchanged key that nobody else in the world knows unless you disclose it to a third party. So that's very powerful technology by itself. But then you basically need to design a lot of hardware to make things like quantum key distribution possible. And so this Nature Photonics paper was basically like showing some basically experimental step forward in terms of various components that would be needed for these sort of things. And so here their concept was actually that you have quantum memories that are happening like at telecom wavelengths around 1550 nanometers, which are, not surprisingly enabled by erbium fiber. So it's kind of analogous to the erbium doped fiber amplifier. But now instead of amplifying classical information, now you can amplify quantum information and also store it as quantum memory. And then they also have some work on basically how to create the entangled photon pairs that I was talking about to ensure that there's a secure exchange of information between the 2 points A and B that are trying to securely communicate. And so the reason why this is so impactful, of course, is that even if you look at classical algorithms for key distribution, it's well known that in principle they can be cracked if they have like a finite length. Usually they're based on the idea of factoring a large number into 2 primes. But if you can guess the prime successfully, either through brute force or some other information, then it's certainly possible to crack them very fast. Whereas in this scenario, it's not possible to do that, at least using any technologies that I'm aware of. So this is like truly secure in a way that RSA and other algorithms are not. So certainly we'll come back to this in more detail since time is up and I see a lot of people are outside. I'll just stop here. Thank you.